Today's lesson is about naming molecules. But before we start naming molecules, it's important to think about how we apply labels to anything in the English language, because it matches up with how we name molecules. So as a warm-up, what would you call this? I mean, I know it's Clifford, but what would you call this if you didn't know it was Clifford? I can tell this is going to be a strong class. In every language, we start by labeling objects with appropriate nouns. We do this exact same thing with organic molecules. If we have a simple organic molecule, we have a simple name that describes the main chain, that is, the most important continuous chain of carbons. Each name we give will have a portion that describes how many carbons. In this molecule, it's hept for 7. Each name or noun will also have a portion that describes what functional groups are present in the molecule. Here it's ane for alkane. The most basic set of skills in naming an organic molecule then are identifying the functional groups and being able to count the carbons that are connected to that functional group. But suppose we have a slightly more complicated thing to describe. We probably don't want to just call this a dog, because it's very clearly a red dog. In the English language, if we want to give a more complicated description of an object, we build up the description by placing adjectives in front of the noun. If we have a more complicated molecule, we're going to build up the name in the same way. We put a descriptor in front of the noun so that we can elaborate it. So here, we have not just a heptane, we still have 7 carbons that are all in a row, but we have a specific type of heptane, a 4-ethyl heptane. The adjective part comes before the main chain and gives information about the location of additional atoms, in this case 4, and the number and type of additional atoms, ethyl. We call this a side chain, and it always comes before the main chain name. I recognize that this additional description coming before the noun is opposite form from some other languages, notably Spanish, so be attentive to this. Chemistry has its own language, and like any language, has a specific syntax. Of course, we can describe adjectives in English language as well, and either with other adjectives that come earlier or with adverbs that also come earlier. So now we have a red dog again, but what kind of red dog? Yeah, it's a barely red dog in the form of adverb, adjective, and then noun. And as you'd expect, if we have a more complicated molecule, we just need to describe anything coming off of our side chains as additional side chains. So here we have a 1-chloro side chain coming off of the ethyl side chain, and the whole thing is coming off the 4th carbon. The chloro describes the ethyl, which describes the heptane. So the general pattern of naming molecules follows the same progression we'd have in the English language. Now we just need to figure out the rules for each part of a molecule's name. The simplest molecules, the straight chain alkanes, have only the noun portion of their name, and the noun consists of just 2 parts. The first part, which is highlighted in red in the second column, refers to how long the molecule is, and the second part, bolded in black in the third column, refers to its functional group. Since we're just starting with alkanes, the second part doesn't change. The prefixes for the first 10 columns are used so often in organic chemistry and commonly encountered molecules that you just need to memorize these. It seems like a list of 10 items to memorize, but the cleverest among you will recognize that the prefixes for 5 through 10 actually match the Latin prefixes used to indicate shapes with a certain number of sides. For example, you probably already know that a pentagon is 5-sided, so it shouldn't be a stretch to learn that a pentane is 5-carboned. My 2-year-old's learning them in daycare right now, so you absolutely can do this. The sooner you can commit this to your memory, the less you'll have to worry about this relatively straightforward aspect of chemistry hindering your ability to learn a lot of more interesting things. You could even stop this lesson right now to learn them so you know the rest of the semester. And since we're learning asynchronously now, it wouldn't matter at all. In fact, I strongly recommend that you do. Here are some line angle structures for straight chain alkanes that you should be able to name at this point. To name these molecules, count the number of carbons to determine the prefix, and then add ane to the end since they're all alkanes. The first molecule has just 1 carbon, so it's meth, and then it's ane. Methane, which is burned to account for about 40% of electricity in the United States and the majority of home heating. The second molecule has 8 carbons. Count them to make sure that you're actually counting correctly. If you only got 7, you're counting the lines rather than the endpoints of the lines. 8 carbons corresponds to the prefix oct, and again we end in ane, octane, as in high isooctane fuel blend, which helps an engine run smoothly. Pause and see if you can identify the names for the remaining molecules. The next molecules in order are ethane, heptane, butane, the compound in lighters, pentane, and decane. Now that you've had a chance to check a few more, what are the last 3 names in order? We have hexane, isomers of which are commonly used as paint thinner, propane, which is naturally a gas but is compressed into an easily transportable fuel, liquid propane, and nonane, a component of lamp oil kerosene. We now know how to name the simplest 10 organic molecules. Great. However, most molecules are not actually these 10 molecules, but are more complex branch-chained molecules. For example, the molecule shown, we can't name just yet because it isn't a straight chain. Like we talked about with naming our red dog, we can create an adjective to indicate the side chain, which will come before and describe the main chain. This will usually need 3 parts. The first is basically how long it is. Since we already have prefixes that indicate length, we can just reuse those, but we'll also need to clarify that the group is a side chain and not another main chain. We'll do that by using YL as a suffix instead of ANE. So while methane is a 1-carbon alkane, methyl is a 1-carbon side chain. So that fully describes the side chain itself, but the other thing that we need is a number to locate it along the main chain. We need to know whether it's attached at the 2nd or 3rd carbon. We assign this number by numbering the main chain so that every main chain carbon has a number, and that the side chain number is as low as possible. So we could number from 1 to 5 starting on the left, the black numbers, or from 1 to 5 starting on the right, the red numbers. For this molecule, we want to start on the left since it gives us a lower number for the side chain, 2 instead of 4. This is a little nitpicky, but it prevents us from having multiple names for the same molecule. This also means that if we're correctly naming a molecule that we think may be the same as another molecule, we can check if they're the same by seeing if they have the same name. Now that we've talked through the rules for naming a side chain, let's see if we can name the whole molecule. We start by figuring out what the longest chain is and how long it is, which we've already identified as a chain length of 5. So the main chain should be named pentane. Next, we're going to name the side chain. In this case, the side chain is the only 1 carbon long. Notice that we only counted the carbon that was not already part of the main chain. We never want to recount a carbon. So a 1 carbon side chain will have the prefix meth for 1 and the suffix il, YL, since it's a side chain, and so it is a methylpentane. While English adjectives come as separate words, in chemistry the adjectives come before the word without any spaces. This is probably related to the German roots for much of organic chemistry, since many German words are built up in the same way. We still need a number to indicate where the methyl is coming off, and so we indicate this with a 2 and then a dash before the methyl. So 2-methylpentane. The 2 is essential here, since there can also be a 3-methylpentane, which is a different molecule. If there's only one possible version of a molecule, like methylpropane or methylbutane, the number is often omitted. So let's do some practice naming molecules with side chains. We'll start off doing the first 2 together. The first step is always to figure out what the longest chain is. We can number from right to left or left to right, and both versions will give us a chain of 5 carbons with a side chain at the 3rd carbon. Notice that we did not start or stop on the carbon that's sticking out where we have the 3 label. That's not because we couldn't. Orientation doesn't matter when we are naming molecules. We didn't start or stop with the side chain because it would have given us a chain of only 4. Now that we have the main chain identified, we need to name it, which you should be able to do. It should be a pentane. A pent for 5, and ane because it's an alkane, only single bonds between carbons. Now we need to identify the side chain, which is just 1 carbon, which should be named methyl. Meth for the 1 carbon, and YL, il, because it's a side chain. This gets listed before the pentane because it describes what kind of pentane we have, a methyl pentane, not just any pentane. Finally, we know that this is different than the methyl pentane that we saw on the last slide. This is a 3-methyl pentane instead of a 2-methyl pentane. We use the number to indicate the location of that methyl. Notice the syntax. The 3 comes before a dash, and then the rest is written all as one word. Okay, on to the next one. Again, the first step is to figure out what the longest chain is. We count from left to right or right to left to get 6 carbons. Using the black numbers from left to right, we end up with a lower number side chain, which is preferred. We could also have counted from the bottom carbon over to the right side and got 6 carbons, and we'd also end up with the same number for the side chain, and that would have been absolutely fine. It would have given us the exact same name. So now we need to name the main chain. It should be a hexane for a 6-carbon alkane. Now we name the side chain, which has 2 carbons. Ethyl, Eth for the 2 carbons and il because it's a side chain. And finally we give the number, 3, because the ethyl is at the 3rd carbon. So the full name of the molecule is 3-ethylhexane. Now you try the next one all by yourself. What is the name of the next molecule on the bottom left? The name is 4-propylheptane. 4 for the position of the side chain, propyl for a 3-carbon side chain, and heptane for the 7-carbon main chain alkane, which we'd number from left to right or right to left. The final molecule is a little more tricky. Remember that you always need to find the longest chain first. For that reason, this is a 4-ethylheptane. If you just count left to right or right to left, you'd only get a chain of 6, but if you count left to bottom, you'd get a longer chain of 7. Since you always need the longest chain, the chain of 7 is preferred, even though it isn't as readily apparent. Remember, the molecules can always rotate freely in space and around most single bonds, so the orientation is much less important in most cases than the connectivity. So what happens if we have a molecule like this? This is a more complex molecule, but we can still just think of it as a main chain with just a few side chains to describe it, like a big red dog instead of just a red dog. We'd start out naming it by finding the longest chain, just the same as always. Left to right gives us a 6-carbon chain with side groups on 2, 3, and 4. Right to left would have given us side groups at 3, 4, and 5, so numbering it from left to right gives us lower numbers and is preferred. I also wanted to note that we could start at the bottom and then continue to the right, and we'd also get 6 carbons. This would not be preferred though, since it would mean that we don't have one of the side chains directly off the main chain, and that would make the name incorrect and also way more complicated. So we're going to number it from left to right. That makes this a hexane. We can also identify every one of the side chains. We've got a methyl at 2, we've got an ethyl at 3, and we've got another methyl at 4. If we have more than one of the same group, we're going to make the name a little bit shorter by grouping all identical side chains together. For example, since we have 2 methyls, we're just going to indicate dimethyl. The prefixes that we use here are the same that you used when naming binary covalent compounds in general chemistry. Di for 2, tri for 3, tetra for 4, and after that they're mostly the same prefixes we use for number of carbons, penta, hexa, etc. We still need to indicate the position of every one of these numbers, even though they're listed together. In this case, we're going to just list 2, 4 before the dimethyl to indicate that one methyl goes at the 2 position and the other one goes at the 4 position. You should have as many numbers as the prefix indicates. So 2 numbers for any di prefix, 3 numbers for any tri prefix. If 2 groups are at the same location, you just list the number twice, so it would be like 2,2-dimethyl. At this point, we have all of the side chains identified, so now we just need to know how to list them. We're always going to list the side chains in alphabetical order based on the name of the side chain, ignoring the prefixes. This means that ethyl will always be listed before methyl, even in cases of dimethyl, because it's the E before the M, we're not comparing it to the D of di. So we'll list 3-ethyl first, and then we'll list 2,4-dimethyl. each describing the hexane. The full name then is 3-ethyl-24-dimethylhexane. Note again the syntax. The numbers are always separated from letters by dashes, but they're separated from each other by commas. The final side chain listed goes directly into the main chain name without any spaces, just like when we had a simple methylhexane. Here are a few problems that have multiple side chains. Again, we'll do one together, then you should try the remaining molecules yourself. Starting in the top left, we have a molecule whose longest chain is 5, meaning that the main chain is a pentane. We have 3 methyl side chains, each one carbon long, and so we're going to use a tri prefix to indicate the number of methyls. Finally, we need a number for every one of those side chains, so we list 2, 3, 4, 2, 3, 4 dash before the trimethyl. Now try to identify the names of the molecule on the top right. The name is 3,3-dimethylhexane. Notice that we use the 3 twice. We need to indicate the position of each methyl even if they're on the same carbon. If you got a different number, try to count out the carbons and label each one to make sure you're understanding how we're counting. Next, try the molecule on the bottom left. Remember to keep the numbers as low as possible. This molecule is a heptane. It has 7 carbons in the main chain. The molecule should be numbered from the right side to the left, which gives us a methyl on the 3rd carbon and a propyl on the 4, for a 3-methyl 4-propyl heptane. Now try the last one. The final molecule is 3-ethyl-2-methylhexane. Notice that the numbers sometimes end up out of order because the groups are always listed in alphabetical, not numerical order. So even though the ethyl comes with 3, the 3 comes first because ethyl comes first alphabetically. Sometimes alkanes are arranged in rings rather than in straight lines. The naming is pretty similar. We just put cyclo in front of the name that we'd give it if it was a straight chain. So a 3-carbon ring is cyclopropane, a 4-carbon ring is cyclobutane, a 5-carbon ring is cyclopentane, and a 6-carbon ring is cyclohexane. Typically, we'll name the rings as the main chain if they're present, particularly in this class. Naming the rings as the main chain usually makes the overall name much more simple and much more straightforward. For example, we typically choose the name cyclopropane as the main chain for a molecule like this, and butyl as a side chain, making the overall name butyl cyclopropane. And this is a little bit more simple than naming it 1-cyclopropyl butane. Often in a ring, we have only one substituent, or side group. Because every position on the ring is the same, any place you could put a side chain would be identical, and we'd typically leave out the numbers. So for this molecule, we'd just give it the name methyl cyclohexane. The methyl is at the 1 position, but we don't need the number because there's no other way the molecule could exist. Putting it any place else would also be a 1 position. There isn't a 2-methyl cyclohexane, so we don't need to differentiate. On the other hand, anytime there's more than one thing attached, we need a number for every side group. That's because as soon as you have 2 groups, you could have a 1,1 version, or a 1,2 version, or a 1,3 version, or a 1,4 version, and they'd all need to be differentiated. We're still going to try to keep the numbers as low as possible, which means that something will always be 1, and we'll just go around in the direction that gives us the lowest number, or numbers if there are 3 or more groups. So that could be clockwise or counterclockwise, it doesn't matter. If it's not clear where to start because of a named functional group in the ring, the group that is lowest alphabetically will always be the lowest number. So here are 2 examples. For this molecule, on the left, we give it the name cyclohexane because it's a ring with 6 carbons. We have an ethyl at the top and a methyl at the side. Because the ethyl is lower alphabetically, that gets to be 1, making the methyl at the 2 position, and the whole molecule then would be 1-ethyl, 2-methyl cyclohexane. The second molecule has 3 methyls, a trimethyl cyclohexane. We can number it starting on the top left and moving clockwise, and that would give us 1, 3, 4. But if we number it from the bottom right and move counterclockwise, we get 1, 2, 4 trimethyl cyclohexane, which has lower numbers overall and is therefore the correct name. One interesting aspect of rings is that bonds can't rotate freely without the ring coming apart. Rings don't randomly come apart, so anything that's on one side of the ring is stuck on that side, and anything on the other side is stuck on the other side. That means that the two molecules shown here, both 1,2-dimethylcyclopentane molecules, are different molecules and need some sort of special designation to differentiate them. We use special descriptors at the beginning of the molecules. This friendly molecule waving on the left is a trans molecule. Trans molecules have groups permanently stuck on opposite sides. I remember this because a trans configuration across a bond looks like an S, where the part labeled in red is the bond in question, and if I placed a pen over the bond, the other two carbons would be on opposite sides of the pen. So we have trans. When we indicate this in the name, we just put the word trans, then a dash before the rest of the name. The molecule over on the right is a cis molecule. Its groups are both on the same side. I remember this two different ways. First, a cis arrangement around a bond looks like a C, and if I put a pen down the red bond, the two groups attached would be on the same side. I also remember alliteratively, cis same side. To indicate this in the name, we just put the word cis and then a dash at the beginning of the molecule. As a reminder, this is a particular of rings, and we'll see it also as a particular of alkenes. It's not something we use for every molecule, only for rings and, as we'll see in the next chapter, certain alkenes. Here are a few rings to practice on. The first ring tests to see if you can number multiple substituents correctly. The second and third, the top right and then the bottom left, are about cis and trans labeling, and the fourth is about singly substituted rings. See if you can identify the names for each of these before you continue. The first molecule is a 1,2,4-triethyl cyclohexane. If you don't see where the numbers come from immediately, we get the lowest numbers in this case if we start at the bottom and go clockwise. I'd also note that these are ethyls, 2 carbons, rather than propyls, 3 carbons. We never count carbons that are part of the main chain as also part of the side chain. This is always true, but for some reason, I've seen students have more problems with it on rings, so I wanted to point that out specifically. The next molecule has 2 side groups very deliberately pointed straight up. This is one way that we indicate whether groups are on the same side or not. Since these are both pointing up on the same side, the molecule is a cis 1,2-dimethylcyclopentane. The bottom left shows another way that we might see cis and trans indicated, by using 3D indicators like dashes and wedges. Remember the bolded lines, the wedges, indicate something coming toward you, while the dashed lines indicate something going away from you. With that in mind, what is the name of this molecule? It should be trans, since the groups are pointed on opposite sides, 1,2-dimethylcyclobutane. The final molecule should actually be easier. It just has one group. Because it just has one group, we don't need a number, and the name is simply propyl cycloheptane. We've mostly focused on carbon groups as side chains. However, there are a lot of other groups that can be named as side chains. Halogens are common side chains in chemistry because they react easily. The halogens are always named as side chains in systematic naming conventions, and they're never going to change the functional group name. So when we have a halogen as a side chain, we just change the ending of the halogen name from ene, as in fluorine, to o, as in fluoro. With that in mind, we can name this molecule. We start out by finding the longest chain of carbons. Make sure you can identify how many carbons are in this chain, keeping in mind that anytime an endpoint is labeled as something else, it's now that thing and not a carbon. So the fluorine is not a carbon. The carbon that the fluorine is attached to is where we start. This is a 5-carbon chain, a pentane. We number it from left to right because that gives us the numbers 1, 2, 3, and 4 instead of 2, 3, 4, and 5 if we numbered from the other side. Again, notice that the fluorine is a fluorine. It's not a carbon and should not be counted toward the length of the chain. We have 4 side groups: fluoro for fluorine, chloro for chlorine, bromo for bromine, and iodo for iodine. We just need to list them alphabetically with the numbers in front of pentane. So 3-bromo, 2-chloro, 1-fluoro, 4-iodo-pentane. Again, remember that the side groups are listed alphabetically, regardless of the number, which is why the numbers are all over the place in this molecule. Now that we've talked about how to name alkanes, this will form the basis for how we name all molecules systematically. We call this system of nomenclature IUPAC nomenclature, since its rules are established in several hundred pages of rules for naming molecules agreed on by the International Union of Pure and Applied Chemistry, IUPAC. From the very simple molecules that we'll name to the most complicated molecules that exist, they all follow the same basic pattern for naming molecules. The first 3 steps are about naming the main chain. No matter which molecule we're naming, the first thing that we'll always do is to find out which functional group is most important. Since we've only dealt with alkanes so far, we haven't really had to worry about this. The alkanes were automatically the most important. But as we continue to add new functional groups, in general, the most recent functional group that we've talked about will also be the most important, the highest priority. The highest priority group needs to be on the main chain and will determine its ending. The second step is to find the longest continuous chain of just carbons, no other atoms, that contains that functional group. No matter what, the functional group needs to be part of this chain, even if it could be longer without the functional group. Our only example of this so far is a ring. The ring is typically named as a main chain, and so a cyclohexane that has a ring of only 6 carbons can still have a chain that's longer attached to it. There are exceptions to this that we won't deal with in this class. Once we have the longest chain connected to the functional group, we'll give it a name that starts with a prefix that indicates the length of the main or parent chain and ends with a suffix that indicates the functional group, which is usually the end of the functional group name. Again, we've only seen alkanes that end in -ane so far, but we'll soon see alkenes that end in -ene, and alkynes that end in -ine, alcohols that end in -ol, and ketones that end in -one, and even carboxylic acids that end in -ic acid. So they're all going to have that ending that indicates the functional group. The rest of the steps are about the side chains mostly. If there's anything that could be in multiple positions on the molecule, we need a number for it. And so the numbering system needs to be consistent for the whole molecule. If there's a group that's higher priority, the functional group that the molecule is named for example, we try to make sure that that number is as low as possible. If there's nothing that's particularly high priority and everything's side chains, like an alkane with just a few side chains, we try to keep the numbers overall as low as possible. At this point, the remaining steps are just to identify the side groups and figuring out which numbers go with each, and then listing them alphabetically, not considering the prefixes di or tri. And finally, we give special descriptors like cis or trans at the very beginning of the molecule. This is the pattern that encompasses all the naming that we've done so far, and it will also extend to everything that we do for naming in the first half of the class, at least the systematic naming. In addition to having our systematic names for molecules themselves, we'll also have a few informal ways of talking about molecules or parts of molecules. We often classify carbons, for example, based on how many other carbons to which they're attached, because this is closely related to their activity. A carbon attached to only one other carbon is often referred to as primary, often indicated with a 1 and a degree sign. These carbons have more space for reactions than other carbons, since hydrogens are small, and often those hydrogens are more easily reacted than other carbons that might be attached. Secondary carbons, indicated with a 2 and a degree sign, are attached to 2 carbons. Tertiary carbons are attached to 3 different carbons. These tend to be less reactive than other carbons because of the amount of space that all those carbons take up, unless the first step is actually removing something. This happens all the time in a full-year organic chemistry course, but is actually fairly rare in this course, and we have just a few examples. Finally, quaternary carbons are attached to 4 other carbons. Generally, carbon-carbon bonds are difficult to react, and quaternary carbons will generally be unreactive. It's really nice and actually really important to have a systematic way of naming all molecules. But many molecules were well known before the IUPAC system was created and widely adopted. Since those names have set in, there's some allowance to use common forms or trivial forms as name as well. Most of the common names that we'll see and used in this course refer to specific arrangements of carbons that would otherwise give us pretty complex names. For example, these molecules are all cyclohexane molecules that have different side chains on them. The side chain carbons are shown in red, and we also show them above, where the squiggly line refers to the side where the side chain attaches to the main chain, but doesn't indicate any carbons. In IUPAC, the side chains all have side chains, which makes complex and convoluted names. Showing just those side chain names and excluding the cyclohexane for space, we'd have a 1-methyl, which would be an ethyl with a 1 carbon a side chain off the first carbon. On the second hexane, we'd have a 1-methyl-propyl on the top left. This name would indicate a 3-carbon propyl group with a methyl off the first carbon. And we'd also have a 2-methyl-propyl on the top right, where the name would indicate a 3-carbon propyl group with a methyl off the second carbon. The final cyclohexane has a 1,1-dimethyl ethyl group because of the 2-carbon ethyl chain with 2 methyls that are connected at the first carbon, hence the 1,1. Hopefully this gives you the general sense that it's pretty onerous to try to name groups in this way. Instead of using these names, we'll often see side chain names that are common instead. Common names are begrudgingly allowed in the IUPAC system nomenclature, but are generally not considered preferred because they can't name more complicated groups without creating an infinite number of names that you'd have to memorize. On the other hand, the common names are a lot easier for small molecules and are used almost universally. Just like the medical professional needs to recognize a common name like Tylenol, even as they may call the drug acetaminophen, we need to memorize these common names to recognize them, even if you prefer to give a correct name without using them. I'm going to talk around these a little bit more than I otherwise might because I know that it can be difficult to differentiate these very similar looking molecules. Pay close attention to what is attached to what and what the names mean. It might make it easier for you because then you can start to assign patterns. First, on the left, we have 1-methyl ethyl is the same as isopropyl in the common form. Again, this is a name that you should memorize, isopropyl. That makes the name of the leftmost molecule isopropyl cyclohexane. Isopropyl is considered one word and it's alphabetized based on the I in iso. Iso in Greek is forked or branched and is used for all groups that have the final carbon move back one position. In this case, the third carbon of that propyl group is moved back from being attached to the second carbon, as in a normal propyl group, to being attached to the first carbon off the main chain. We also end up with much simpler names for the 4-carbon side chains on the center molecule, with the 1-methyl-propyl group on the left becoming sec-butyl, and the 2-methyl-propyl group becoming isobutyl. Notice that the sec-butyl is listed as 2 words. That's actually alphabetized based on the B in butyl rather than the S in sec, unlike isopropyl and isobutyl, which are one word and alphabetized as I. Sec here is short for secondary, referring to the fact that it is still a 4-carbon chain just attached at one of the secondary carbons instead of at the first carbon of the chain. And just like before, isobutyl is a chain where the final carbon is moved back one, in this case from being attached to 3 to being attached to 2 instead. Our final common side chain is tert-butyl, which is like sec-butyl written as 2 words and alphabetized based on the B of butyl. Tert is short for tertiary, referring to the fact that our 4 carbons are arranged in such a way that they're attached to the main chain at a tertiary carbon. One of the first places that we see these common side chain names used is in the common form for names of haloalkanes, that is, alkanes that have halogens on them. IUPAC only accepts halogens being named as side chains, but it's still fairly common to see the halogens treated as main chains with any carbons coming off the side named as a side chain instead. In this form, the halogen main chain is given the same name it would have as an anion. The ene is switched to ide. And the common side chain names are always used when we're using the common forms, as opposed to IUPAC for naming these molecules. So for example, the first molecule on the left in IUPAC would be named 2-fluoropropane, but in the common form is named isopropyl fluoride. So the fluorine becomes ide in this case, and we use the common side chain name as an additional word to describe the fluoride. See if we can identify the names of the other molecules shown using the halogen as the main chain name and then indicating the side chain. This will also give you another chance to look at the connectivity of these commonly named branched side chains. From left to right, we have sec-butyl chloride, isobutyl bromide, and tert-butyl iodide. So that's it for this lesson. Tune in next time to learn about physical and chemical properties of alkanes.